morning, gentlemen. Assalamu alaikum. This is Muhammad Khurshid Alam, Assistant Professor, Department of Electrical and Electronics Engineering, American International University, Bangladesh. Of course, doing PhD in UMP, Malaysia, Pahang. Today's topic: optimal power flow solution incorporating stochastic wind power generation by Moth flow optimizations. Next 10 minutes and so, I'll cover the following: optimal power flow problem formulations, MFO and GW for optimal power flow solutions, findings from simulations, test equipment, gust of wind, optimal power flow, total transmission loss minimizations, finally conclusion, of course, at last question and answer sessions. The power system benefits from optimal power flow, a crucial optimization tool for planning and operations. Without altering voltage management, the optimal power flow strives to reduce power distribution losses and the cost of electricity pulled from the substations. Because of the integration's complex difficulties it presents, the optimal power flow has been a popular topic among power system research companies all around the world since it was first introduced more than 50 years ago. The optimal power flow is defined as a single or multi-objective issue of reducing fuel expense, pollutions, transmission loss, voltage deviations, and other costs with limits on generator capability, line capacity, bus voltage, and power flow balance. The optimal power flow programs helps the electrical network run more effectively and affordably by determining the ideal settings for control variables. Now, why this research? That means contribution of this research. The following are the study contributions. A new MFO algorithm is being created to handle the optimal power flow problem. When incorporating MFO into a well-known IEEE 30 bus architecture, the erection nature of wind power is considered. C. Analyzing the optimal power flow solution fields for MFO and GW statistically and in comparisons. And finally, combining the decrease of voltage variations and MFO loss into a single optimal power flow solution goal. Now, about the optimal power flow problem formulations. Inequity restrictions may also be represented in terms of operational constraints, as we can see here, a generator cost curves for single and multi-objective fuel choice. Constraints for the generators: there are restrictions on how much actual and reactive power may be generated, as well as how high generator bus voltage can be. Now about the MFO, the most remarkable aspect of Moth is their ability to navigate at night. They have figured out how to fly at night using moonlight. They used a method known as a transverse orientations to navigate as shown in the figure. Always it is showing the in directions to the light. A Moth flies by maintaining a constant angle with the moon, which is a very efficient technique for transferring long distance in a straight line. As you can see, the gray wolf optimizations, hunting activities seen in all packs, a vision being purchased by a pack of 9 wolves in Yellowstone National Park, as in the screen. Number 1, there is here a 9 wolves, 1, 2, 3, 4, 5, 6, 7, 8, and there are 9 wolves. Approaches, chase. This is the approaches, this is the chasing, and this is the tracking mode. Then finally, it is pursuing harassing and encircling maneuvers, that is in the B, C, D, and also finally the Ols at E resting at the end of hand in a final stationary arrangement that resembles a regular polygon. Now about the findings from the simulations. The available probability density functions as in the figure used to mimic wind distributions, whereas a log normal PDF in figure here is used 3 heat generators, 2 wind generators, and 1 PV solar array make up the upgrade networks. Here is the test equipment, that is a simple IEEE bus. The case study for this topic used to modified versions of IEEE bus test systems. 3 thermal generator plants are replaced with 3 wind farms with capabilities of 50, 40, and 40 megawatt at bus 5, 11, and 13. Now, rest of wind, the wind speed is expressed using the variable probability density functions as was previously explained. The wind speed is indicated in this article using a scale parameters value of 15 and a shape parameters value of 1.75 for 1000 samples of wind speeds are generated randomly using variable parameters. The frequency distribution for each parameters wind and wind turbine generator across 1000 random samples as shown in this figure. Optimal power flow, that's the results. Values for the number of generators, generator bus voltage, and transformer tap ratio should be all be optimized in the optimal power flow. Table 1, that is summary of the optimal power flow findings. Due to their low cost of productions, the generators in the slack bus and bus 2 produce more output than the other generators. Notably, GW and FO closing numbers were 7.09 and 7.08 megawatt respectively. As observed, GW and MFO both offers voltage profile on the load buses that are vary from 0.9 to 1.05. This demonstrates that the voltage profile of the systems are more reliable than those obtained using MFO. Although GW has produced a worse results than MFO, all algorithm convergence with 2000 iterations, and therefore this is still true. Voltage distribution across all techniques load buses, as we can see for MFO and GW. The voltage profile of the load buses for each approach is shown in figure. In this scenario, the targeted function is to lower overall transmission losses. The overall losses calculated using Moth power following the executions of the load flow programs. The control variables and state variables for each approach all fall within the predetermined limits. Now about the conclusion, the problem of optimum power flow for a network containing wind farms is tackled in this research. With the transient and permanent outage of lines in the transmission systems, this study discussed the decrease in losses and increases the dependability. To achieve the paper's goal, each line is switched off or the least amount of loss possible followed by the load buses. Except for the slack buses, all buses are bound to constrained active power. Therefore, marginal losses during switches will be provided by the slack buses. The study conclusions show that the MFO method is superior when compared to the approach's results. According to the pattern created by the chosen PDF functions and the related parameters, alternating the PDF parameters of questionable sources also alters the generator cost. When a carbon price is accurately accountable for in a case study, the contributions from clean energy sources are at their most productive. In terms of the needs of the power system, cases studies for the highly nonlinear optimal power flow with statistical source model are also satisfactorily satisfy the constraint management technique. So that's all from my side, gentlemen. Now, if you have any questions, you can ask me.